Hi, my name is Harlan. Welcome to the H. Matricon Mechanical Engineering channel. Our topic for today is hydraulic calculations for fire sprinkler systems. Supposing you have a manufacturing plant in Ontario and they are going to construct a building expansion adjacent to the west side of its existing process building. The floor area is 3,087 square feet. The occupancy hazard classification, according to an FPA 13, is ordinary hazard group 2. The sprinklers had been laid out in one of our video tutorials entitled Layout of Fire Sprinkler Systems. And let us also assume that the designer has already chosen the pipe sizes detailed on the next slide. This will all be steel pipe schedule 10. Note that in a previous video tutorial, plotting the design area and a fire sprinkler layout, we have already established the design area. So this layout here shows the sprinklers, the branch lines, and we have the pipe sizes, and we have the lengths here, and it shows the boundary of the design area. So from the area density curve in NFPA 13, we chose a density of 0.2 GPM per square feet at 1,500 square feet. So from here, this is the curve for the ordinary hazard group 2, and we chose the sprinkler operation area of 1,500 square feet. We have a density of 0.2 GPM per square feet. Then we number the nodes in the design area, starting with the most remote sprinkler, going upstream until we reach the bottom of the sprinkler system riser. Then we select the sprinkler orifice. So we choose K equals 8.0. Then we determine the largest area covered by any sprinkler in the design area. This is taken from the layout, and we determined it to be 129.87 square feet. And multiply this result by 0.2 GPM. So the discharge of the first sprinkler will be 129.87 square feet times 0.2 GPM per square feet. It will be equal to 25.97 GPM. And so from this, we can now solve the pressure of the first sprinkler using the equation Q sub 1 equals K times square root of P sub 1, wherein Q sub 1 is 25.97 GPM, and we have a K value of 8.0, so P sub 1 will be equal to 10.54 PSI. So here, this is now your layout with the numbers. 1 is the most remote sprinkler. NFPA 13 sets a minimum pressure of 7.0 PSI to ensure a proper spray at the sprinkler orifice. If the calculated pressure obtained in the previous step is 7 PSI or less, then we replace the sprinkler orifice with a smaller value of K. Let us now analyze pipe number 1, which is the portion of pipe from node 2 to node 1. The water flowing through the portion of pipe will be equal to the discharge of the sprinkler at node number 1. So Q of pipe number 1 will be 25.97 GPM. And we are going to solve for the pressure drop of pipe number 1 using Hazen-Williams equation as shown. From table 27.2.4.8.1 and FPA 13, the Hazen-Williams C value for black steel pipe for wet sprinkler systems equals C is equal to 120. The inside diameter of a 1.5 diameter steel pipe, schedule 10, is a 1.682. The length of pipe number 1 from node 2 to node 1 is 12 feet. Hence, the pressure drop at pipe number 1 can be calculated to be 0.25 PSI. To get the pressure at node number 2, we will simply add 0.25 with the pressure at node number 1. We will add because we are going upstream. So 10.54 plus 0.25, the result will be P sub 2 is 10.8 psi. So from this value, we can now calculate the sprinkler discharge at node number 2. So we have the K value of 8, the P, and we have P sub 2 is equal to 10.8. So Q sub 2 will be 26.29. The next step is to analyze pipe number 2. And the water flowing through that portion of pipe will be the sum of the discharge of sprinkler at node number 1 and the discharge of sprinkler at node number 2. So 25.97 plus 26.29. The result will be 52.26 gallons per minute. And the length of pipe number 2 is 12 feet. So we can now solve for the pressure drop of pipe number 2 using Hazen-Williams equation. And the result will be 0.93 psi. And again, we are going upstream. So we add that to the pressure at node number 2. So 0.93 plus 10.8. The result of the pressure at node number 3 will be 11.73 psi. So from this pressure, we can now solve the sprinkler discharge at node number 3, 8.0 times the square root of 11.73. Q sub 3 will be 27.4 gallons per minute. Then let us go now to pipe number 3, which is a portion of pipe from node number 4 to node number 3. And water flowing through that portion of pipe will be the sum of the discharge of the 3 sprinklers, nodes 1, 2, and 3. So 25.97 plus 26.29 plus 27.4, the total will be 79.66 GPM. And we will use that value to calculate the pressure drop of pipe number 3 using Hazen-Williams equation. And the result will be the pressure drop between pipe or the pipe between node number 3 to node number 4 will be 0.6 psi. And again, we're going upstream to solve for pressure number 4, P sub 4. We will add the pressure drop of 0.6 psi to the pressure at node number 3, 11.73 plus 0.6 psi. The result at node number 4, the pressure will be 12.33 psi. So the sprinkler discharge can then be calculated. 8.0 times square root of 12.33. It will be equal to 28.09 GPM. Let's go now to pipe number 4. The water flowing through that portion of pipe will be the sum of the discharge of sprinklers at nodes 1, 2, 3, and 4. So 25.97, 26.29, 27.4, and 28.09 GPM. The total will be equal to 107.75 GPM. And the size of pipe number 4 from node 5 to node number 4 is 2-inch diameter, and it is 6 feet long, and it has a 2-inch T. So we use the equivalent length modifier from NFPA 13 here. So it gives us the equivalent length of a schedule 40 fitting that we will use for this one, this expression here. Okay, so number 5, we have a T here. So 6 feet, and this one is 2.157 divided by 2.067 raised to the power 4.87 times 10 feet, so 18.31. So we will use that equivalent length, 18.31, and the Q is 107.75, and then the diameter will be 2.157, and the result of the pressure drop between node number 4 to node number 5 will be 1.6 psi. So again, we can solve for pressure at node number 5 by adding that pressure drop of 1.6 to the pressure at node number 4. So 1.6 plus 12.33, the pressure at node number 5 will be 13.93 psi. So we tabulate the results here as shown, so that you will have an idea. And let us now analyze pipe number 6, which is the portion of pipe from node 6 to node 5. The discharge of the sprinkler at node number 6. Again, we will have to start with the largest area covered by any sprinkler in the design area, 129.87 times the density of 0.2 GPM per square feet, 25.97. So from this, we solve the sprinkler pressure. So K times the square root of P sub 6 will be equal to Q sub 6. So we have the value of Q sub 6 here, 25.97, 8, and then we can solve the value of P sub 6 will be equal to 10.54 pounds per square inch. So the water flowing through the portion of pipe will be equal to the discharge of sprinkler at node number 6. Q 6 to 5 will be 25.97. And the length of pipe from pipe 6 from node 6 to node 5 is 6 feet. However, you use the equivalent length modifier, and the result will be 15.90 feet here from 6 to node 5. And using the Hazen-Williams equation, we can solve for the pressure drop of pipe number 6 to be equal to 0.34 psi. So again, since we are going upstream, we add the pressure drop of 0.34 rather, to the pressure at 0.6, 10.54 plus 0.34, the result will be 10.88 for P sub 5. But take note, we have now two values of P sub 5. The first value is 13.93, and what we have solved now is 10.88. That cannot be. There should be only one pressure in that junction. So we will choose the larger value and readjust our calculations for that branch there from node 5, node 6. So we will adjust the flow of Q6 5, 25.97 using the equation flow adjusted divided by the computed flow, which is 25.97, is the ratio of the higher pressure to the lower pressure, 13.93 and 10.88 here. So in square root, the result will be 29.4 GPM. So that's the flow. The flow will be 29.4 GPM going to node 6. And so the discharge of the sprinkler will also be equal to that value. And the pressure drop of node 6 at node 6 will be 29.4 here, and the equivalent length of 15.9 rather, the pressure drop from node 5 to node 6 will be 0.42 psi. So from that, since we are working our way downstream, the corrected pressure at node number 6 will be equal to P sub 5 minus the pressure drop between 0.6 and 0.5. So 0.42 will be subtracted from 13.93, though the pressure at 0.6 or P sub 6 will be 13.51 psi. Let us counter check. You have Q6 will be 29.4, and then the K value of 8. Let us see based on this equation. So we double check P sub 6 is equal to 13.5 psi, which is correct. And then we tabulate the results here. So now let us go to this branch line here from node 7 to node 11. Determine the flow. Oh, by the way, we have to solve first and we have to analyze first the pipe from node 5 to node 11. So we have 107.75 plus 29.4. The total flow at for pipe junction 5 to 11 will be 137.15 GPM, and the length of pipe from node 5 to node 11 is 10.5, and using the equivalent length modifier, the equivalent length is 30.66 feet for the 3-inch pipe, and the pressure drop can now be calculated, and it will be 0.56 psi. And since we are going upstream, we add that pressure of 0.56 to 13.93, and the resulting pressure will be equal to 14.49. So again, we will plot it here in our table. Now, let us analyze the branch between node number 7 to node number 11. This is identical to that of line 1 to 5. Therefore, the preliminary calculations will be the same as what we did before. So these are the results here. That is identical. And we notice that there will now be 2 results for the pressure at point 11. We have now 13.93 and 14.49 psi. So this cannot be the case. There should be only one pressure in the junction. So we will adjust the flow. Okay. So from this equation, the adjusted flow divided by the calculated flow of 107.75, that will be a ratio of the higher pressure, the square root of the high pressure to the lower square root of the lower pressure. So Q sub 10 to 11 adjusted divided by 107.75, square root of 14.49 divided by the square root of 13.93, and the adjusted flow from Q10 to Q11, A 109.9 GPM. And so we can calculate now the pressure drop. So using 109.9, and for junction between 10 to 11, and the pressure drop will be 1.66. And then we are going to go this time downstream. So what we will do is subtract 1.66 from 14.49 psi, and the result will be 12.83 psi. And from this, we can solve now the discharge of the sprinkler at node number 10. 8.0 times the square root of 12.83 will be 28.66. And we subtract it from 109.9, the resulting flow of pipe number 9 will be 81.24. Use this to calculate the pressure drop between node 9 and 10, and the result will be 0.62 psi. And then, since we are again going downstream, we deduct this pressure from pressure number 10, which is 12.83. So 12.83 minus 0.62, P sub 9 will be equal to 12.21 psi. So from this value, we can now solve the sprinkler discharge at node number 9 to be 8.0 square root of 12.21. The result for the sprinkler discharge at node number 9 will be 27.95 gallons per minute. So the corrected flow at pipe number 8 will be equal to 81.24 minus 27.95. The result will be 53.29. So recalculate the pressure drop of pipe number 8 using the flow of 53.29 GPM, and the result will be 0.96 PSI. And again, we are going downstream, so we subtract this value from P sub 9, 12.21 minus 0.96, and the resulting value for P sub 8 will be 11.25. And in the same manner, you calculate the sprinkler discharge of node number 8, 8.0 times the square root of 11.25. The result will be 26.83 GPM. And subtract that value from 53.29, which we got earlier, and the result will be from the flow for pipe number 7 will be 26.46 GPM. And we can now, using this value, calculate the pressure drop up at pipe number 7 using the Hazen-Williams formula. The pressure drop from node number 7 to node number 8 is 0.26 PSI. And again, we are going downstream, so we deduct this pressure of 0.26 PSI from P sub 8. So 11.25 PSI minus 0.26. The resulting pressure P sub 7 will be 10.99, and the sprinkler discharge at node number 7 can be calculated at 8.0 times the square root of 10.99. The result sprinkler discharge for node number 7 will be 26.52 gallons per minute. So we can now tabulate it in our table, the results. And then since we have now solved up to here, the next step is to solve this branch from 12 to 11. In a similar manner that we have analyzed from 6 to 5, the preliminary calculations will give us these values here. So again, there will be two values of P11, 14.49 and 10.88. This cannot be. There should be only one pressure at the node. So we use the larger value and adjust the flow of pipe number 12. Okay, so using 25.97 and this formula here, Q sub 12 minus 11 divided by 25.97 is the ratio of the square roots of the higher pressure to the lower pressure, and Q sub 12 to 11 adjusted will be equal to 29.97 GPM. And the discharge of the sprinkler at node number 12 will be Q12 29.97 GPM. Using that value, we can calculate the pressure drop at pipe number 12 using Hazen-Williams formula, and the result will be 0.44 PSI pressure drop. And again, we are going downstream, so we subtract that value from 1449. So 1449 minus 0.44, the result for P sub 12 will be 1405. Let's counter check using the formula Q sub 12 equals K square root of P sub 12. So we know Q sub 12, we have calculated it 29.97, the adjusted flow, and we have the K value of 8, and the result will be P sub 12 will be 14.03 psi, a very minimal error. So this is correct. And we tabulate the results. So the next step is to determine the flow from node 11 to node 14. So we add all the flows from between 5 to 11, the flow from 10 to 11, and the flow from 12 to 11. So 137.15 plus 109.9 plus 29.97, the result will be 277.02. Solve for the pressure drop of pipe number 11 using Hazen-Williams equation, and the resulting pressure drop will be 2.0 psi. So we can now calculate the pressure at node number 14 by adding the pressure drop of 2.0 to P sub 11, which is 14.49, and the result will be P sub 14 will be equal to 16.49 psi. We can now tabulate the results. The next step is to solve the branch between 13 and 14 here. Okay, 13 and 14. So repeat the calculation procedure as we did for the preliminary calculations, and the results of P14 will be 10.67 psi, and there will be now two values again. P sub 14 will be 16.49, and the calculated 10.67. This cannot be. There should be only one value of pressure. There should only be one pressure in the node. So we choose the larger value and adjust the flow. So using this formula, ratio of the square root of the high pressure to the square root of the lower pressure, and we have the flow of 25.97 GPM. So the adjusted flow will be 32.28 GPM. And from that adjusted flow, we will calculate the pressure drop using the Hazen-Williams formula, and the result will be 0.21 psi. And again, we are going downstream. So the corrected value of the pressure at node number 13 will be 16.49 minus the pressure drop of 0.21, and the result of P sub 13 will be 16.28. And from this value, we can calculate the sprinkler discharge at node number 13, 8.0 square root of 16.28. The resulting sprinkler discharge at node number 13 will be 32.28. So we have now solved this one here. And let us now analyze the branch between 16 to 14. We repeat the calculation procedures that we did for the preliminary calculations, and we got the results of P sub 14, 11.64. So again, there will be two pressures, so you adjust the flow of this branch using the higher pressure and this ratio here. So this value is the adjusted flow divided by 52.22 GPM, and it will equal to the ratios of the higher pressure to the square root of the lower pressure. Square root of 16.49 divided by the square root of 11.64 will be Q adjusted flow from 14 to 15 will be 62.15 GPM. And the pipe length is 1 foot and 5 inches. And using the equivalent length modifier, the equivalent length will be 11.32 feet. So recalculate the pressure drop of pipe number 15. using the adjusted flow of 62.15, we will have the pressure drop will be equivalent to 1.2 psi. And again, we are going downstream, so we deduct the pressure from 16.49. So 16.49 minus 1.2, the result will be 15.29 psi. Solve for the flow at 15 will be K square root of 15 adjusted. So 8.0 square root of 15.29 will be 31.28 psi. So we subtract it with 62.15, the resulting flow from pipe between node 16 and node 15 will be 30.87. That will be the adjusted flow. And using that value, we solve now for the pressure drop of pipe number 16 using Hazen-Williams equation, and P sub 15 to 16 adjusted 0.32 psi. And again, we are going downstream, so we subtract the pressure drop of 0.32 from pressure at node 15. So 15.29 minus 0.32 will be 14.97 psi. So we solve for the sprinkler discharge at 0.16. Will be K times the square root of pressure of 16 adjusted. So 8.0 square root of 14.97 will be 30.95 psi. We can now tabulate our results here. Yeah. So we have now solved this branch, and now we will proceed to the pipe between junction number 14 and junction number 17. So to obtain the flow from node 14 to node 17, we add the flow from node 11 to node 14, and plus the flow from node 13 to node 14, plus the flow between the node 15 to node 14. So 277.02 GPM plus 32.28 GPM plus 62.14 GPM, and the result will be 371.44 GPM. And the length of pipe from node number 14 to node number 17 is 9 feet. And using the equivalent length modifier, the equivalent length will be 29.16 feet. And then we can solve the pressure drop of pipe number 14 using the flow of 371.44 and equivalent length of 29.16. So the pressure drop will be 3.4 psi. So we can now solve the pressure at node number 17. So what we will do is we will add the pressure drop between node 14 to node 17, which is 3.4, to the pressure at node 14. So 16.49 plus 3.4, the resulting pressure for P sub 17 will be 19.89 psi. We are adding this. Why? Because we are going upstream. And then we will tabulate the results. So we will continue working our way upstream until you reach the bottom of the system riser. So I think this explains the procedure, how the hydraulic calculations for the fire sprinkler systems are being done. Although there are a lot of computer systems or software available for computing the hydraulics for fire sprinkler systems, I also have my own program. I use my own program. It is important that you also understand how it is being done, manually. So I hope this explains the method well, and thank you for watching, and stay tuned for more video tutorials at HMatchCon Mechanical Engineering channel on YouTube. Thank you. Bye now.